Good afternoon, everyone. Today we will finish section 3, axioms of probability, a little quick, and then we will start section 4, some simple propositions. Now, last time we introduced those 3 axioms. Okay, we introduced those 3 axioms, and we define the. Here, let's write some note. Okay, let's make some note. Try to review those. So here, S is the sample space. Oh, here. So S is the sample space notation, which lists all, which is the set of all the possible outcomes for an experiment. Then E is any event. Okay, any event. Or any subset, right? Any subset from the sample, out of the sample space. Now, we define the probability of any event by those 3 axioms, okay? By those 3 axioms. And last time we introduced the probability is the limiting relative frequencies, right? And if we follow those 3 axioms, and then we should be able to understand what does probability means. Okay, so probability of the event should be a number between 0 and 1 and can equal to both sides. And axiom 2, the sample space equals 1. Okay, the sample space, the probability of sample space equals 1. That is with the probability 1, the sample space would always occur because the sample space consists of all the outcomes, right? All the possible outcomes. Axiom 3, for any sequence of mutually exclusive events, E1, E2, until the infinite number of events. And we understand what is mutually exclusive event. If the I and the J, the index are different, then the intersection of those events, the intersection of any of those 2 events will be the null event. Okay, null event. Then the probability of the union of all those sequence of events, that will be the sum of all the probability for each event. And we know PE is the probability of the event E, okay, of the event E. Now, let's take a note, okay? Let's take a note for those 3 axioms, okay? For those 3 axioms. So, the first one, okay? The first one, the probability that the outcomes of the experiment should, probability of an event is some number between 0 and 1, okay, between 0 and 1. And we can understand from the NE over N, right? The number of event in the event E over the total number of outcomes in sample space. And then axiom 2, okay, let's write axiom 2. Let's make a note, okay, let's make a note. Let's talk about one by one. Axiom 1, the probability of the event is between 0 and 1, can equal, right? Can equal. And you can think about those with the number of event E over the number of outcomes in event E over the total number of outcomes in the sample space, but we understand that the probability gives the limiting, right? The limiting of this relative frequency as n goes to infinity. And I think this is easy to understand, and we can verify everywhere in the examples we did about probability, right? Axiom 2, then the outcome, okay, the outcome will be a point that illustrates the outcome will be a point in the sample space S. That means the probability of the sample space occurs is 1. Because no matter what outcomes you get, this outcome will be 1. No matter what outcomes you get, that will be included in the sample space. So that means the sample space will always occur, right? Any outcomes occurs in the experiment that is included in the sample space. So the probability of the sample space equals 1. Now, we are going to talk about axiom 3 in a specific way, okay? In a specific way. Let's explain what does this notation mean. What does this notation mean? The probability of the union, infinite event union, right? So that is the event sequence E1, E2 until E, the index can go to infinity, right? I from 1 to infinity. So this probability denote there is the outcomes will occur in any event, right? In any event, E1, E2, E3, at least in any one. Make sense? So these outcomes, okay, this is also an event. And I think we illustrate we explain the union of two events, right? Two event means the outcomes occurs either in E1 or in E2 or in both. What does this mean? So that means the outcomes will occur at least in any one of those events, right? So it's the same here, okay? It's the same here. So that will be the outcomes. I'm talking about the event first. The outcomes occur in at least one of the event. At least one of the event. One of those events, okay? At least one of those events. E1, E2 until infinity. It can occur in 2 events, in 3 events, but it should at least occur in one of those events. Make sense? So that is the outcomes. So what does this probability mean? So this probability means the probability of the outcomes occurs at least one of those events, right? Occurs at least one of the events. And then that equals the right side. What is the right side? The summation 1 from the index 1 from infinity probability of EI. What does this part mean? This part, the right side, and I already explained what is the left side, right? The left side is the probability of the event. What kind of event? The outcomes will occur in at least one of those sequence events, right? One of those sequence events. So the probability of this new event, this is also a new event, okay? This one is also a new event. The probability of this one, that equals the sum of each respective probability. Each respective probability. That is what does this axiom 3 means. And we are going to look at two special cases, okay? Two special cases. And based on the mutually exclusive we are talking about. So let's talk about case 1, okay? Case 1. Here we know we have a sequence of events, right? Now I can let the sequence of event, a sequence of event E1, E2 until infinity, right? Now case 1 I can do in this way, okay? I let the first event is the sample space, and then the others, okay? The other event, EI, is the null event when I is greater than 1. What does those notation mean? So I give the special case, okay? I give a special case for the sequence of those events. And we know those events are mutually exclusive, right? Which means the index, if the index are different, those events, the intersection of those two events will be null event. Now, I let my first event is the sample space. That consists of all the possible outcomes. Of course, trying to become the mutually exclusive, the other event should be the null event, right? So the other event, which means when I is greater than 1, E2, E3, the other event, they are all null event. Now, this is the special case, right? This is the special case. Now, so that is event. By the way, in this case, what is this union? What is this union? EI. Let's call someone to answer the question. What is this answer? What is this one? The union of all those EIs. What is this event means? Let's call someone. This student, 60013. 60013, this student. So if we know the first event is the sample space, the other events are all null events, then what is the union of all those events? What is the union of all those events? No one is following me in the rain classroom? All right, let me continue here. So according to Axioms 3, the probability of this union, all those unions, that will be the sum of each one, right? Each one. The sum of the probability for each one. So that will be P probability E1 plus probability E2 and plus PE3 plus all those, right? Plus all those. Now, let's answer this question, okay? The students are not available. So, if we let E1 is the sample space, the other events are null event for I is greater than 1, then the union of this event is the sample space, right? Is the sample space, of course. So, the sample space, so the left side is the sample space probability. And then, how about here? PE1, what is my E1? My E1 is PS, right? This event is especially the sample space. Sample space is also called a special event, right? Which consists of all the possible outcomes. And then that becomes from I starting from 2 to infinity, and then PEI, right? Starting from I sorry, I starting from 2 to infinity, the probability of all those events, the sum of all those. Now from here, probability of sample space, probability of sample space. That means, and by the way, those are all the null event, right? Those part are all null event. This part, it's the sum of all those null event. Null event. So what is the probability of the null event? 0, right? This implies the null event has the probability 0, okay? The null event has the probability 0, okay? Has probability 0. So from here, okay, from here we put the special case 1 we called here for the sequence of events in this way, okay? And case 2, we can take finite, okay? We can take the finite case, okay? We can take the finite case. So we can let the event a null event for I is greater than n. And we know for those ei, if they are null event, right? For those index I is greater than n, that is the null event. And we know the probability of the null event is 0. So in this way, that means we only have from 1 to n event, okay? According to Axiom 3, we can rewrite the probability of the union of n event, right? Null event is there is no outcomes, right? There is no outcomes included in the null event. So from 1 to infinity, we can rewrite as from 1 to n. We only care about the first n event. That will be the sum of I starting from 1 to the n probability of I index starting from 1 of n. Because the others, if you are going to plus, sorry, it's not plus. If here is union, okay, the original one will be the union, right? Will be the infinity. It doesn't matter to infinity for this special case. Yes, for the case 2, if we let the I is null event for I is greater than n. So here this one equals, we only care the finite case, the first n event, because starting from n plus 1, n plus 2, those events, they are null events, so there is no outcomes included. So the union of this one will be the same as the union of this one, right? And according to the axioms, according to the axioms 3, that will be the sum of I from 1 to infinity, right? I from 1 to infinity PEI. But we know that we only care about those, right? We only care about the first n because the like P E n plus 1, P n plus 2, those event, okay? Those event probability will be 0 after n, okay? After n, those probability event will be 0. So the sum of infinity becomes the sum of I from n. And actually, this is the finite sequence, okay? This is the finite sequence. And here, this finite sequence event E1 to E2 to En are mutually exclusive, of course. are mutually exclusive. Those n events are mutually exclusive. What does mutually exclusive mean? EI does not equal to J. Event EI intersect event EI and EJ are null event, right? There is no outcomes included in the intersection of any of two events. They are null event. We just let them in this way, okay? We let them in this way, and those can become all the sample space, okay? Become all the sample space, and we will discuss those in the next section also, okay? In the next section also. Now let's look at two easy examples. Example 1. If our experiment consists of tossing a coin, and if we assume that a head is as likely to appear as the tail, then we should have the probability. So here it's easy, right? Tossing a coin. So sample space. What is my sample space? Tossing one coin. So the sample space would either be head or tail, right? Sample space only included in the two outcomes, and we assume a head is the same as the tail. So the probability of a tail equals the probability of a head of getting the outcomes, right? Getting these outcomes. So be careful about your notation, okay? We are not supposed to write in this way, okay? We are not supposed to write in this way, because here we should include it. We should write here as an event. This one you write. That means H is an event. Okay, is not an outcome. Be careful of your notation. We write probability of capital letter E. That means the probability of event E. So here, this H and T means the outcomes in the sample space. That denotes the outcomes. Okay, we get this outcome. It's also a special event, like the event head occurs. And what is event E? Event E is this outcomes H, like that. Okay, so this is like P, event probability of event E, and you can also define tail occurs as another event F. So be careful of the notation. Without the curly bracket, that means the event. Okay, that means the event. So that is you have the same chance to get a head as well as a tail. If that is the assumption I usually mention, if the coin is made balanced, okay, balanced on both sides. If it's unbalanced, or if the coin were biased, we might get the head with the higher probability than the tail, okay, And we can simply verify that. We can simply verify, or to check the axioms, okay, to check the axioms. Number 1, the probability of any event should be a number between 0 and 1, of course, right? Should be a number between 0 and 1, and can equal to those two numbers, no problem. And then axiom 2, the probability of the sample space. The probability of the sample space is always 1, right? The probability of the sample space equals 1, because you will either get a head or tail, right? You will either get the outcomes that included in the sample space. So the probability you get both. You will get either one of them is 1. And then let's check the axiom 3, okay? Let's check the axiom 3. We can write event E1 is the outcomes head, and event E2 is the outcomes tail. What is the relation between E1 and E2? Of course, E1 and E2, they are null events. They are mutually exclusive, right? Now let's apply the axiom 3 when we only have two events, okay? when we only have two events, that is E1 union E2, that will be the probability, the sum of PE plus the sum of E2, right? The sum of E2. And by the way, what is E1? What is E1 union E2? That is the sample space, right? That is the sample space. And what are those? No matter it's balanced or unbalanced, it's always 1, right? No matter which case, okay? No matter which case. So it's very simple example, and we can verify with those 3 axioms. Now let's check example 2. It's die rolling. If a die is rolled and we suppose that all 6 sides are equally likely to appear, then we would have the probability of getting each number is 1 over 6. Okay, assume that the 6 sides are equally to appear. From axiom 3, it would thus follow the probability of rolling an even number. So we are going to define the event, okay? Or you can write some other notation, event A. I can write my event A, capital letter. So that will be the even number occurs. Even number occurs. We are going to work out this probability of event A. Even number occurs. What are the outcomes including in the event A? So all the possible outcomes, of course, here sample space will be 1, 2, 3, 4, 5, 6, no problem, right? You are going to get one of those 6 numbers if you are rolling a die. How about the event A, even number? You get 2, 4, 6, right? 2, 4, 6 in this way. 2, 4, 6 in this way, right? Then what is the probability? What is the probability of event A? The probability of event A, we can represent event A in this way. You get 2, 4, 6. You are going to get 3 outcomes. 3 outcomes. So those 3 outcomes are mutually exclusive. Okay, you can name it as each event, like E1 is you get 2, E2 you get 4. Not disappointed. What does you mean? We can go back. Okay, you can review those notes later. So we can mark the event E1, E2, E3. Okay, E1, E2, E3. We can name those events. So the probability of event A, that will be E1 union E2 union 3. We can write in this way. Let me write here. That will be the union of yi from 1 to 3 ei, right? And then, of course, those 3 events are mutually exclusive. When you get the outcome 2, then the number is not going to show 4 and 6. You only get 1, right? When the number is showed 4, you are not going to get 2 or 6. They are mutually exclusive because one time you only get 1 numbers. So they are mutually exclusive. Then, according to axiom 3, those is case 2. Okay, case 2, finite sequence of the event. Finite sequence of the event, the probability of the union of 3 events, that will be the sum of 3 probability for each event, right? So will be probability of E1 plus probability of E2 plus probability of E3. What is the answer? I believe everyone should be able to get the answer, but we follow the axiom 3, which is 1/2, right? No problem. The calculation is pretty easy to get this probability. And can you think about the probability of getting an odd number? If I define the So question, okay, question. You can think about this one. Question: if I define the event B is the odd number occurs, what is PB? What is the probability of event B? PB. And can you follow the Axiom 3? We in the probability course, work out the probability is one part. Okay, another part is trying to understand the way we describe as event, and we can follow the axioms. Okay, we can follow the axioms to calculate the probability. Okay, because this is the simple one. You can just calculate like 1/6 plus 1/6 plus 1/6, you get 1/2. That is pretty easy to calculate. But some more complicated case, you should define the mutually exclusive sequence of events, E1, E2, like that. Then follow the Axiom 3, you should be able to work out the problem. Okay, and again here, okay, we are done section 3. Okay, we are done section 3 about the axioms. Okay, about those 3 axioms. Yes, probability of event B is 1/2. It's the same. Okay, it's the same. And we can interpret this in a different way. Okay, we can talk about later in section 4, the event A and B. So here, those 3. Let me come back. Okay, let me come back to the axioms. Okay, let's come back to the axioms. So in section 3, those 3 axioms, at the very beginning of this section, we mentioned what is the axioms. Axiom is the self-evidence, right? Self-evident evident statement. So we are not going to strictly prove it. We believe, we accepted those 3 axioms are true. Okay, without any proof. And with this way, okay, with this way, we can call probability is the function actually. Okay, probability is the function, and those 3 axioms are very important. And also you can read it in the textbook. Okay, read it in the textbook that constitute the modern mathematical approach to probability theory. Okay, to probability theory. And also here, follow those 3 axioms. The probability, okay, the probability is the set function. P kind of set function. It's a function, okay, based on the event, right? Based on the event. And what is the event? Basically from mathematics, it's a set, right? It's subset of the sample space. So the probability is the set function that is defined on the event, right? Defined on the event, which is the subset of the sample space. And we understand those 3 axioms, it's self-evident. We are not going to prove those. Okay, we accepted it's true. Okay, without any proof. And it's in accordance with our intuitive concept of probability as related to chance and randomness. Okay, as related to chance and randomness. I think it's easy to understand. The chance you get when you're tossing a coin, the chance you get a tail is 1/2 if it's balance made. The chance you get a head is 1/2 in that way, right? In that way. So here, okay, here that is the axioms of probabilities in section 3. Okay, in section 3. Let's take a break. Then we can continue we can start section 4. Okay, let's take a break.